A real value function of several variables is a function whose domain is in Rn and the codomain is the real numbers. So it's a function whose images are going to be real numbers, but the inputs, the pre-images, are going to be points in Rn, in R2, R3, or in general Rn. So, for instance, if we have a function from R2, a function f that goes from R2 to R, so these are the kind of functions that actually we're going to be able to draw, since observe that in order to draw the domain, we need to have enough dimensions to draw also the codomain. So for instance, in the original functions that you are familiar with, that goes from R to R, so we need one R for the domain and another R for the codomain. So in our cases, we are going to need now, for functions of several variables, we're going to need already two variables for the domain. So two versions of R in the domain, and then another version of R for the images here. So the domain of our function is going to be contained in this plane, and the images are going to be in this axis as a regular function from R to R. So for instance, if we have a function from R2 to R such that to x, y associate certain operation between x and y. So for instance, 3 multiplied by x plus y squared. So how do we graph this function? Well, the idea is that our tables is going to have values for x, y, but then we're going to have an x-axis for the actual output, that this is going to be the z-axis here. So the x and the y are going to be for the points in the domain, and the z is going to be for the result, for the output. So for instance, in this case, let's give some values here. For instance, when x is 0 and y is 0, let's say. How much is z? Well, we do the operations here. 3 times 0 is 0, plus 0, 0 will be 0. So that means that for the point 0, 0 of x and y, we are going to have that the value of z is 0. So the first point of our graph is going to be a 0, 0, 0. So if we give other values here, so for instance, let's give the value 1 for x and let's say 0 for y. So what will be the value of z? Well, we do the operations here. 3 times 1 plus 0 squared. So the result will be 3. So then we have that the value of z here will be 3. So then our next point is going to be value of x is going to be 1, value of y is going to be 0, so this is the point of the domain, and we are going to go then in the z-axis until the value 3. So this is the next point of the function. So we are trying here for some kind of drawing in the three-dimensional space. So I want to emphasize that when the domain is R2, the function, actually the graph of this function lives in R3. So we need one more dimension to draw this function. And the graph of a function of two variables is going to be called surface. So in general, having the same system that we have before with x, y, and z. So our function, when we draw all the points, is going to look like some kind of surface like this, to be something like that. So let's see, for instance, this particular example. This is an example of another function from R2 to R again, where this function, what it does is this in here. So take an x and y, and that's minus x squared minus 2y squared. Well, again, given values to the function as we did before. I mean, given values x, y, and find out the value of z. So you could see that the graph of this function is going to look like something like this in this window. We can here see the axis, so this will be the z-axis. So we have here the x and y axis. So we can see, for instance, that when x and y was 0, z in this case was 0, 2, and so all the other values when we put different values of x and y in the domain. So we can observe how this surface looks like from different viewpoints, and you can see here the values of x and y that correspond to this particular window where we're seeing this particular piece of this surface. To calculate the limit of a function of several variables, I mean these functions, in order for us to be able to draw are going to be functions of two variables, but we can expand and we can generalize to functions of any numbers of variables, 3, 4, 5, n variables, even though we cannot actually draw because we have just a three-dimensional space where we can draw functions, graph functions. Okay, the definition of a limit of this function of two variables when x, y approaches to this particular point, AB, this particular point in the domain, which is R2. So this will be the notation for the limit. We have now that two variables here, x, y, approaches to AB. And we are going to say that this limit is equal to L in case that for any epsilon there exists a delta such that for any point close to delta, the image of the point is close to L. So this is the familiar definition you know from Calculus 1, only that this idea of closeness to a point, we have to think now in several dimensions. So if we have, again, our system of references with x, y, and z, and we have here a surface as before. So what we are saying here to calculate the limit when x, y approaches to certain point AB, so let's say that this is here the point AB. So what we are saying here is that in order for this limit to be actually L, so what have to happen is that if we take here any point xy close to AB, so what this thing is going to mean is like a ball here around AB. If we take any point in this neighborhood and we do the images of these points here, what have to happen is that these points here really end up in a neighborhood here of L of distance no more than epsilon. So it's the same familiar definition of limit, only that the intervals that we normally have in the x-axis get replaced by this kind of disk where we consider they are the neighborhood of AB, all the points around. And to calculate the limit of a function of several variables is in general much more complicated than in one variable. But let's say in a case like this one, for instance, let's try the limit when xy approaches to 0, 0 of this function. So the function minus x squared minus 2y squared. Well, let's substitute x and y by 0, and we get here minus 0 squared minus 2, 0. So this is 0 minus 0, which is 0. So in this case, by just plugging in, we are able to calculate this limit and is equal to 0. So let's try this other problem now. So that will be the limit when x, y goes to 0, 0 of the function y over x now. So in this case, when we try to plug in here, we get that this is 0 over 0 is undetermined. So the problem with several variables is that all the methods that you have to leave indeterminations in one variable are not going to work for several variables. So it's much more difficult in several variables to calculate how much is a limit. By the other hand, it's easier to calculate or to decide that a limit does not exist. So if you have to prove that a limit does not exist, so you can apply certain techniques and you can prove that. If you want to prove or calculate a limit, so then you will mostly have to go to the definition of the epsilon and delta that I mentioned before. So why is the proving that a limit doesn't exist is easier? Well, if you remember the system of references that we drew before, so if we have a surface here and we are trying to calculate the limit at a certain particular point. So in one variable, we have to prove that the limit from the left and from the right coincide. So in this case, the problem is, as I said before, the neighborhood of a point if all this. So there is no left and right there. So in order to calculate that the limit exists, you will need to calculate that in all possible directions the limit is the same. Meaning that if you approach to this point in this line, or in this line, or in this line, or in this line, or in this line, you get always the same result. But also if you approach in this curve, or in this curve like this, or if you approach like this, so it will be impossible to calculate the limit in all the possible ways that you have to approach to the point AB. So to prove that a limit exists by checking the different directions is just not possible. So it would be impossible to check all the directions. But if you are able to prove that in at least two directions you obtain a different number, so then the limit cannot exist. So that's why it's easier to prove when the limit doesn't exist than to prove that the limit does exist and is equal to something. So for instance, suppose that you find a line here that the function approaches to 3 and another line that the function approaches to 5. So then the limit cannot exist because you found two different directions in which the limit is different. Okay, so let's see in this case if we can try for that. I mean, to try to prove that this limit actually does not exist. And so we are going to try to approach to 0, 0 in different directions. So let me draw just the domain here, the x and the y. And we are trying to approach here to 0, 0. So let's approach, for instance, with this line, with this direction. So this direction is the line y equal x, right? So the 45 degrees. So let's calculate the limit restricted to that. So let's calculate the limit when xy goes to 0, 0, but when y is equal to x. So if y is equal to x, we are going to have here x. So that will be x over x. So x divided by x is 1. So the limit when y goes to 0, 0 of the number 1 is just 1. So we calculate that if we approach to 0, 0 in this direction, the limit is 1. So let's see if we approach to the limit in another direction. For instance, let's approach by the x-axis. So let's approach in this direction. So let's calculate the limit when xy goes to 0, 0. But now in the x-axis is the function, the line y equals 0. So let's put here y equals 0. We have 0 over x. So then this is the limit when xy goes to 0, 0, or 0 over x. 0 over x is 0. So the limit when xy goes to 0, 0 of the function 0 is 0. So we got that in two different directions in which we approach to 0, 0, we got different numbers. So because these two numbers are different, so the limit doesn't exist. So this limit does not exist, because if it were to exist, in all the directions should be the same. But remember that this is a method that works to prove only that the limit does not exist. If we get here the same number, for instance 1 and 1 in both directions, it means nothing. It means only that when we are approaching in this direction and in this direction, in both directions the limit is 1, but it could be that there are other directions that is different. So that's why just to have 2 things or 20 things or a million directions in which the limit is the same is never enough to prove that the limit is that number. Instead, when we find 2 that are different, it's enough to prove that the limit does not exist. Well, the continuity of a function in a particular point is defined the same that is defined for one variable. So we have to have existence of the limit, and the limit have to be the same that the value of the function at the point. So for instance, let's see that we have a function that is defined in this way. First, we need to calculate the limit, see if that limit exists. So let's calculate the limit of 3x squared plus 3y squared divided x squared plus y squared when x, y goes to 0, 0. Let's calculate this limit. This is 0 over 0, but we can see easily that the denominator is actually 3 multiplied by this divided by this. So we can cancel, and we can see that this limit is actually equal to 3. So we prove that the limit is equal to 3. And the function, how much is f evaluated as 0, 0? Well, according with this definition, when x and y is 0, 0, is the other y's part, right? Because this definition is when x, y is not 0, 0. So when it is 0, 0, the function is equal to 1. So we got that the limit is 3 and the value of the function is 1. So these things are not equal, and so we can deduce that then this function is not continuous at 0, 0. So as I said before, we can extend this to functions of more variables. So in this case, for instance, a function of 3 variables, if we want to calculate the limit when x, y, z goes to 1, 2, 3 of this function, which is this one, so we calculate the limit of this over x. Let's substitute, and we will have here 1 plus 2 plus 3, and everything divided by 1. So the result of this limit will be 6. The concept of derivative in several variables is more complicated than in just one variable. We are going to start by defining what is called a partial derivative. And essentially, a partial derivative is going to be a derivative in the direction of the x-axis or in the direction of the y-axis. So if we have in the domain the x and y-axis, so we can calculate the derivative in this direction or in this direction. And this is what they are going to be called the partial derivatives. This is going to be the notation for the partial derivative of the function f with respect to the x-axis, so with respect to the variable x. And the definition of the derivative in that direction is going to be the familiar definition of derivative that you know, but the increment is going to happen only in the variable x. So, and then we're going to make this increment going to 0 as is common in the calculation of the derivative. The partial derivative of f with respect to y is the limit where the increment then is going to happen in the y variable. So this is the common notation for partial derivatives with respect to the variable x and with respect to the variable y, but they are not the only ones. So this other notation is also very common, so you can just put the name of the function and put a subindex x or subindex y for the derivative with respect to y. And so let's see how do we actually calculate these derivatives. So let's calculate the derivative of this function with respect to x. To calculate the derivative with respect to x, we are going to consider that in the function the only variable is x. So every time that appears y, we are going to consider y as a number. So in this case, you will consider x squared minus xy. Y is like a number, minus 2y, and y is like a number again. So let's consider that when calculating the derivative. So the derivative is going to be, the derivative of x squared is 2x minus the derivative of xy. Y is a constant, goes out of the derivative, and the derivative of x is just 1. And so here minus 2y. Well, y is a constant, 2 is a constant, the whole thing is a constant, so the derivative is 0, and the derivative of phi is also 0. So we have that here the derivative is just 2x minus y. Okay, so let's do the same now for the derivative of this function, but now with respect to y. So we are going to consider now this function as a function of y only. So every time that x appears will be a constant, will be considered as a constant. So in that way, the derivative of x squared is just 0 minus the derivative of minus xy. Well, minus x is a constant that goes out of the derivative, and the derivative of y is just 1. And then minus the derivative of 2y is 2, and plus the derivative of phi, which is 0. So this derivative is just minus x minus 2. So these are the two partial derivatives of this function. We have also, once that we calculate one derivative, we can calculate the second derivative, or the third, or the fourth. So the calculation of the second derivative, this is just applying the same thing again. So this is about the notations for these derivatives. So this notation, second derivative of f with respect to x and y, is actually, and this is the important part here, this is the definition, is the derivative with respect to x of the derivative with respect to y. So meaning that you have to calculate this derivative, and when you are done, that will be a function, then you do the derivative with respect to x of that. And observe the order of the variables here. Fix this one here. Second derivative, this is the correct notation, second derivative of f with respect to x twice, or second derivative of f with respect to y twice. So what this thing is, for instance, the last one, you do the derivative of f, the first partial derivative of f with respect to y, and you do it, when you get the result, you do it with respect to y again. So, for instance, one more thing, this is an alternative notation for this derivative that is also very common to use. Very important to pay attention to the order here, since it's different, the order in which you write in this notation and the order in which you write in this notation. This one, what it's saying is that you do the derivative y first and then you do respect to x. Well, this is exactly what it's saying, this one here. X is the last one that you do, y is the first one you did. So both say the same thing, but observe that the position of the order is different, right? So you say here xy, and here you say yx. So pay attention to what notation then you are using to understand in what order to do the derivative. So let's calculate the second partial derivatives of this function. We start by calculating the derivative respect to x. And so this is going to be respect to x. Remember that x is the only variable here. So it's going to be the derivative of a product, will be the derivative of the first one, which will be 1 times the second one as it is, plus the first one as it is, times the derivative of the second one. That will be e to the 3x plus y times 3. So taking here common factor, this will be equal to 3x plus 1 e to the 3x plus y. Okay, and let's do now the derivative of f with respect to y. This is going to be the derivative of the first. So now observe that in order to calculate the derivative respect to y, this function, this variable here is a constant. So the constant is going to go out, just out, and we're going to do just the derivative of e to the 3x plus y, that is itself. Observe that in this case, in the second case, was not the derivative of a product because it was just a constant multiplied by a function. Okay, so then these are the two first derivatives, derivative respect to x and derivative respect to y. Okay, so now we are going to do the derivative of f respect to y respect to x. This is equal to the derivative respect to y of the derivative respect to x. And see that this is important to recall the definition here, because this is a function that you have to look for. Where is it? Is this one, right? So then this is the function that you have to do the derivative respect to y. And then the derivative respect to y of this one, this is a constant now, so the constants go out, 3x plus 1, and times the function e to the 3x plus y, and times 1 by chain rule. So this is then the second derivative. Let's calculate the second derivative in the other order, the derivative of f respect to x respect to y. So this is going to be the derivative respect to x of the derivative respect to y. So this is the derivative respect to x of, and the derivative respect to y is this one. So we are going to write x e to the 3x plus y. And we are doing the derivative respect to x, so then this is going to be a product derivative here, right? So let's do this product derivative. Times 3 by the chain rule, and taking common denominator, common factor here would be 3x plus 1 e to the 3x plus y. Okay, so this is the derivative that we obtain, and see what we have obtained before. This. Well, when we observe this one, they happen to be the same, right? We obtain them in a very different way, right? You see that the operations that we are doing are completely different, but we obtain the same result. Well, this is going to happen in general. So we have a theorem, the mixed derivative theorem, that says that if all these derivatives here are continuous, so are always going to coincide. So you can calculate. I would always actually recommend to calculate in both ways, because if you don't get the same way, so that will be a check that you are doing something wrong somewhere, right? So then you can go back and check.